Hello and welcome to SWAT Spot with me, Andy Staines. I'm going to talk today about a problem that I set for our apprentices on Friday, and I gave them a couple of problems, so I thought I'd talk about the best way of solving the problem. So let's have a look at what we were dealing with. So I gave them this circuit. They'd previously done a parallel circuit separately and a series circuit. We're both dealing with same values, 100 volts as our supply voltage and 25 ohm resistors. So they were able to solve two 25s in series and two 25s in parallel, but I've given them this and it really did seem to throw them a curveball. So let's have a look at what I would see as being the best way of solving it. Now, there are always more than one way of addressing these kind of problems, but this is what I would choose. I might see if I can give you some options along the way as well. So, what did I ask them to find? Well, first of all, I asked for RT, total resistance. I then asked for IS, supply current. I asked for the current through each resistor, so IR1, 2 and 3. And I asked them for the voltage across each resistor, voltage R1, voltage R2, voltage R3, the power in each resistor, and then the total power, PT. So looking at what we've been given to start with, we have VS, our supply voltage, we have our value for R1, R2, R3. It's a DC circuit. We are assuming that the wires have no resistance or that it's negligible. So we're just going to deal with the resistors themselves. So that's our starting point. So let's see at how you would look at this. So one of my key recommendations is whenever you have a problem like this is that you start out with what you do and what you don't know. Okay, if you don't know where you're at, then you're not going to be able to get very far. So R1, R2, R3, RT. We also are looking for IS, IR1, IR2, IR3. We are looking for V. We already know VS, so we'll put that down. VR1, VR2, VR3. We are looking for power then, so power total. Power resistor 1, power resistor 2, power, power resistor 3. So what do we actually know? What do we know and what don't we know? So we know R1, we know R2, we know R3. Don't know RT, IS, any of the currents. We do know VS. We don't know the rest of this. But looking at this, we are only looking at R's, I's, V's and P's. So in terms of the formulas we're going to use, it's actually not that huge amount of different formulas. So let's look at first of all our simple formulas. V equals IR. Well, that wraps up or ties together three of those pieces. We also know that P equals IV. So voltage is equal to current times resistance and power is equal to current times voltage. Now, those kind of tie together, don't they? So there's no P in the top one, there's no R in the bottom one, but the top one has got I and V as the bottom one does, and likewise we've got an I and a V in here. So current and voltage are common to both formulas. It's just we have resistance here and power there. So that's going to be useful. We're then going to need our formulas for working out total resistances. So there are two formulas. When we're dealing with a series circuit, it's very easy. RT is equal to R1 plus R2 plus R3. Okay, so it's the arithmetic sum. Okay, we just add them together. Parallel circuits, and this is a little bit more tricky and one that often gives people problems. 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. That can be difficult because this doesn't give you RT is the answer, it gives you 1 over RT as the answer. So whatever you get from adding 1 over R1, 1 over R2, 1 over R3, that is 1 over RT. To find RT, you've got to divide that result by, into 1, and that will give you the answer. So RT is equal to 1 divided by 1 over RT. And that's a real head scratcher. But we'll look at how we'll solve that as we go forward. Okay, so this is what we do know. This is what we don't know. These are the formulas. So let's move on to our next page. Simplify. Now, because this is a series parallel circuit, we have to simplify it before we can start to solve it, because you can't work out parallel and series together. You have to solve either the parallel bit first or the series bit first, depending on how it's arranged. Now this circuit, I would call this it's parallel before it's series. Okay, so overall we've got 2 parallel networks, but one of them has got resistors in series. So let's just put our values there. Excuse me. R1, R2, R3. We won't worry about the numbers just for a minute. But because this is overall parallel, we have to solve and simplify the series bit first, which is actually the easiest thing to do. So what we can say is R1, 2, so this is the resistance of resistor 1 and resistor 2 combined, is equal to R1 plus R2. So let's put those values in. R1, 2 is equal to 25 plus 25. R1, 2 is equal to 50 ohms. Excellent. So what we can do, we can actually get rid of this at the top, and we can just look at it very simply as being a single resistor of value 50 ohms. So this is now R1, 2. Okay, so let's just put those values in there. 50 ohms and 25 ohms. So now what we got is a 50 ohm resistor and a 25 ohm resistor in parallel with each other. So let us look at this. So RT is equal to, now what I'm going to use here is a slightly easier format for solving a parallel circuit, where instead of using 1 over RT, 1 over R1, I'm going to use RT to the power of minus 1, R1 to the power of minus 1, etc. It's called the reciprocal, and it can be found on your calculator by looking for the x to the power of minus 1 button. Okay, so let's just draw that up there on your calculator. It will look like this, x to the minus 1. Okay, so if you press a value and then you press x to the minus 1, that is just like dividing 1 by that value. So RT, I'm going to open a pair of brackets, is equal to R1, 2, okay, raised to the power of minus 1, plus R3, raised to the power of minus 1. And then we take that sum and we raise the sum to the power of minus 1. So put the values in. RT equals 50 to the minus 1 plus 25 to the minus 1 raised to the power of minus 1, and that means RT is equal to 16.67 ohms. Okay, so that is the answer for this section. So that's our RT. We've solved that. Right, let's move on to the next bit. So always simplify. If it's overall series, you solve the parallel parts first. If it's overall parallel, you solve the series parts first. That's really important. Okay. Next, solve the problems in order. So we solved our RT. So we can say that RT is 16.67 ohms. Now we're going to look at the other bits on the formula, the next section. So we needed to find our current, IS. Well, IS is simple. IS is equal to VS over RT. So current supply, the total current leaving the battery in that circuit, is equal to the battery voltage divided by the total resistance, assuming there's no other internal resistance in the battery or resistances in the wires. So IS is equal to 100 divided by 16.67, and without getting my calculator out, I'm pretty certain that is 6 amperes. Okay, so there we have our value, 16.6 amperes. Let's move, 6 amperes from 16.67 ohms. Let's move on to the next. We want to look at the current through each branch. Now, on a circuit like this, we have a split. So the current, the current leaving the battery, IS, splits. Some of it goes this way and some of it goes that way. So there is actually a branch, isn't there? A forking of the ways. So we've got IR3 going this way, and we've got IR1, 2 going this way. Remember, current is common in a series circuit or in a series part of a mesh circuit. So a mesh is a way of describing this sort of circuit where you've got some series and some parallel. And then the current will recombine. It comes back together here to return to the battery. Okay? So current is equal to voltage over resistance, and that's what we are going to use here. So I equals V over R. So IS we already have. R3, that's a nice easy bit to solve, we'll do that first, is equal to the voltage over R3 divided by R3. And if we look at that first page again, we can see that R3 is directly connected to the 100 volts. There's nothing else in the way. So that's really nice and simple. So let's go back to our page here. Let's put our values in. IR3 equals 100 divided by 25. IR3 equals 4 amperes. Nice. Okay, let's look at the next one. IR1, R2. So it's the voltage across as the current passing through those two resistors. So it's the voltage across those two resistors, and of course those two resistors as a series part of the parallel circuit have the supply voltage across them. Which means, and we're going to have the total resistance of those, R1, R2, so that the value of R1 and R2 added together. So IR1, 2 is equal to 100 volts of supply voltage dropped over those total resistances, which is 50 volts. IR1, 2 equals, well, funnily enough, 2 amperes, and that's good. I said the current splits, doesn't it? 6 amps splits. Got 4 amps down one branch and 2 amps down the other branch. So that's nice. Let us move on to our final bits and pieces. Voltage. Voltage is equal to current times resistance. We know the current, we know the resistance. So voltage R1 is equal to the current through R1, which was 2 amperes. Sorry, let's just put the proper bits of the formula in there. IR1 times R1. Okay, and IR1, the current through R1 is the same as the current through R1 and R2. So VR1 is equal to that 2 amps times 25. VR1 is equal to 50 volts. Okay, and VR2 can be the same. VR2 is IR2, which again is the same as the current through R1 times R2. VR2 equals again 2 times 25. VR2 equals 50 volts. And we said VR1, well, it's equal to the supply voltage because it's directly connected. So VR1 equals 100 volts. I've been Andy Staines. Thank you very much for watching. If you've got any questions or any suggestions of any further videos I can do, please put them in the comments or send me a message. And please, if you can, like, subscribe and share the videos. Here's my Instagram link and my YouTube bit.ly link, short URL. Thank you very much.